Thank you for joining us for Elements of Image Quality, Part 1, Resolution, Unsharpness, and Magnification. My name is Dr. Holger Roth. I am Application Engineer and Global Application Trainer at Waygate Technologies in Germany. Before we begin, we want to cover a few housekeeping items. At the bottom of your screen, there are multiple application engagement tools you can use. All the engagement tools are resizable and movable, so feel free to move them around to get the most out of your desktop space. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A engagement tool. We will try to answer these during the webcast, but if a fuller answer is needed or we run out of time, it will be answered later via email. Please know we do capture all questions. A copy of today's slide deck and additional help materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Here we see 4 images of the same object. Aluminum wires of an image quality indicator on an aluminum plate. I guess you would agree the lower left image is the best. It is sharp and of low noise. The one in the upper right is unsharp and noisy, no doubt. The others are sharp but noisy or unsharp and smooth. So why not just stay with the best? The answer is, as in many fields, quality is also a matter of cost and time, which in industry is almost the same. So we do not need always the maximum image quality, but the appropriate image grade. For example, the upper right is 100 times faster and much cheaper than the lower left. Therefore, we need quantities to describe image quality for process definition and acceptance. Today in part 1, we talk about sharpness. To explain these effects in quantity systematically, we will introduce total unsharpness and resolution and show how to measure total X-ray system unsharpness and basic spatial resolution and how this is done in computed tomography images too. We shall explain the relation between these quantities, unsharpness, basic spatial resolution, and NTF. And we shall outline the measurement of detector basic spatial resolution, SRB, and of the X-ray tube's focal spot size. We shall study how to use that to predict total image unsharpness in an X-ray system. And finally, we will check what else could affect resolution. Before we go on, we would like to hear something from you now. If you are operating an X-ray system, do you monitor the image quality of your system? So first, we need to clarify, what do we mean when we talk about unsharpness or resolution? Unsharpness may be described as the capability of an X-ray system to differentiate periodic line patterns of strongly absorbing material. The fineness of the pattern is measured in line pairs per millimeter. Note that one line pair consists of a transparent and a non-transparent line of the same width. Since we can see these single lines when the pattern is resolved, we may call the width of the single line the basic spatial resolution. So there is a factor of 2 between unsharpness and basic spatial resolution. It is important to understand that for measurements of unsharpness and resolution, noise effects need to be suppressed. So unsharpness should not be confused with detectability because noise and unsharpness together limit the detectability. To illustrate the effect of unsharpness, we display here the same pattern with increasing unsharpness towards the right. As you can see, not only the edges of the lines become fuzzy, but also the contrast is reduced until the pattern becomes an unstructured gray spot. So in terms of detectability, unsharpness reduces the contrast. Up to now, we are dealing with intuitive but physically vague concepts. A good way to define a physical quantity, for example, in a standard, is to clearly describe a measurement procedure. In the following way, you use well-described tools under well-defined conditions and read certain results. You process these results so and so, and the result is the defined quantity given as a number and a unit. And in good practice, also with an error estimation. This error estimation can avoid overreacting if there is a slight change between measurements. The standards ASTM E2002-15 and ISO 19232-5 specify a procedure to measure total image unsharpness as well as basic spatial resolution. Let me outline the main features of these standards. They first define an image quality indicator named duplex wire gauge. This object consists of pairs of parallel wires, so-called elements, of stepped diameters with gaps of the same diameters in between. Here you see an X-ray image of such a duplex wire gauge on the left-hand side. It's slightly tilted to avoid aliasing effects. On the right-hand side, you see a cross-section to a pair of wires with the three equal diameters or gap distances. As said before, the wire diameters are stepped. Here you see the list as you find it in the standard. The duplex wires have numbers D1 up to D13 and diameters from 0.05 millimeters to 0.8 millimeters in a logarithmic divided scale. As you see, the width of a line pair refers to the unsharpness value, second column, and the width of a single wire to the basic spatial resolution in the image, the orange column. The reciprocal of the unsharpness value gives the line pair value or maximum resolved spatial frequency in line pairs per millimeter. This column number 4. The measurement procedure is as follows. We put the duplex wire gauge onto the designated sample position between the X-ray source, or focal spot, and the detector. On the detector, we get a magnified image. Magnification, by definition, is the ratio of image size and object size, which is the ratio V of focus detector distance and focus object distance. This digital image is taken and stored under the conditions given in the standard. The resulting image may look like this. For evaluation, we select the region of interest of a prescribed width aligned perpendicular to the wires. The pixel values are averaged parallel to the wires to reduce noise and eliminate aliasing. In this way, we get an intensity profile. Now, this intensity profile may be evaluated in 3 different ways. Applying the simplest method, we would just look for the thickest duplex wire. We cannot differentiate anymore. This would indicate the total image unsharpness visual. A more quantitative method would be to use 2 duplex wires to interpolate to the fictive duplex wire with exactly 20% modulation. I will come back to what this means later. The third, more stable method uses several points with a polynomial interpolation, as we shall see on the next slides. For this method, we plot the intensity curve as a function of the position on the duplex wire gauge. This is the reason why we need also the magnification to know how wide is a pixel on the object scale. Now we calculate the modulation. We read the height of the dip in between the 2 wire shadows of each duplex wire. Then we read the depth of the shadow of the two double X wires. Then we divide that by the dip height we measured before and plot the results in percent as a function of the double X wire spacing. See the right-hand side diagram. Then we fit the polynomial of rank 2 to these data points and look for the 20% intersection. This position is the basic spatial resolution in the image. In this case, it is 202 microns. Here, look at the intersection of the red line and the green line. The total image unsharpness is twice as much, 404 micrometers. For the 20% method I mentioned before, with linear interpolation, we would have used the second and third point in this case from the left. For sure, it makes sense to estimate the trueness and precision of such a measurement to tell real changes from measuring artifacts and statistics. This was the way to determine the basic spatial resolution in a radiograph. For a CT image, the resolution of the radiograph is just the best possible case because it is based on these radiographs. But there may be further blurring factors from reconstruction, filtering, and imperfections in the sample manipulation. It makes not so much sense to scan, for example, the double X wire gauge, because it is very difficult to evaluate in a CT slice and sometimes even very difficult to scan. For this purpose, ASTM E1695 uses a different, more elementary approach I will describe now. This method is based on the evaluation of the MTF from a tomographic slice of a rod or a disc. The unsharpness in the 3D image on the CT slice manifests in any physical sharp edge in the object. As a phantom, the standard defines a rod of application-specific material and thickness. The rod is scanned being aligned to the rotation axis. Main requirement to the phantom is its circularity, so that the slice images do not remarkably deviate from a circle. As a first step, we determine the transition from material to air as a function of the radius of the rod slice. To suppress the noise, we average along the parameter of the disk. The precise mathematical procedure is quite stable and described in much detail in the standard. The result of this procedure is the averaged intensity course across the edge of the disk, the edge response function, ERF, the dotted line in the left-hand side diagram. The derivative after the distance from the edge is the line spread function LSF, the bell-shaped curve. This describes how the intensity profile of a very fine line would look like. So the LSF describes, so to speak, the shape of the unsharpness. The Fourier transform of the LSF is the modulation transfer function. It describes which percentage of a given contrast is transmitted through the system as a function of its spatial frequency in line pairs per millimeter. It's the line at the right-hand side of the diagram. In other words, it describes how finer and finer patterns lose more and more contrast. As the limit of visibility, 10% contrast have been defined. So the spatial frequency at which the MTF reaches 10% is the spatial line pair resolution. It's reciprocal the total image unsharpness, and half of that is the basic spatial resolution in the image. Here we have a real measurement example as generated by the software delivered with Waygate Technologies systems. The MTF equals 10% at 7.02 line pairs per millimeter. Hence, the total image unsharpness is 142 micrometers, and the basic spatial resolution is half as much, 71 micrometers. The physical limit would be the Nyquist frequency, which is indicated in red, as given by the detector pixel pitch. We would like to use the opportunity to ask you, have you heard about the ASTM standard E1695 measurement of computed tomography system performance? Or have you ever used it? Now we used and explained the terms unsharpness, basic spatial resolution, and MTF 10% value. They originate from the same physical phenomenon, and the standards are made such or defined such that at least most of them correspond to each other. For your convenience, we compiled a table displaying the conversion formula. In this table, you can look up all the relations between the three quantities. By definition, the basic spatial resolution and unsharpness are related to each other by a factor of 2 or 1/2 respectively. Correspondingly, both values are related to the reciprocal MTF 10% value, which is measured in line pairs per millimeter. Sometimes people are a bit confused because the MTF is measured at 10% and the SRB modulation is measured at 20%. This is intended and just guarantees that they describe the same state. We now know how to measure unsharpness and resolution in a CT slice or in a radiograph. In case, for example, these values would not meet the specs, or you are to build a system or to choose a system or are to define exposure conditions, it would be important to know what are the physical causes for this unsharpness. From the side of the system, these are mainly detector basic spatial resolution and the tube's focus spot size. Let's start with the detector basic spatial resolution, SRB. ASTM standard E2597 defines a method to measure the detector basic spatial resolution. It is very similar to the practice E2002, which we used to measure the total unsharpness. In this case, we just put the phantom, the duplex wire gauge, directly onto the detector to have magnification 1. Also, we put it on an angle of 2 to 5 degrees to the X or Y direction to avoid aliasing effects. Here you see the geometric relations. We just put the gauge directly onto the detector to have magnification 1. So the object scale is identical to the detector scale. Further, as we shall see later, at unity magnification, the influence of the tube's focal spot is null, so that we can really measure the pure resolution or unsharpness of the detector. The evaluation procedure is the very same as in ASTM E2002, which we use to determine the total image unsharpness. We evaluate the modulation and fit a polynomial of rank 2 to the data points. From the intersection with the 20% line, here the green line with the red line, we read or calculate the detector ISRB, which is then, here in this case, 202 micrometers. Now the question could be, how is this related to the pixel size? This table shows some major detector specs for several types of detectors. Here we focus on the SRB and the pixel size delta P highlighted by this yellow box. One might think now the SRB should be just the pixel size or very similar, since the pixel size is the physical base of the resolution. However, in most cases, it is greater than the pixel size because of the internal unsharpness of the detector, which is mainly caused by light scattering in the scintillator. This effect tends to be worse for powder scintillators than for cesium iodide scintillators, which consists of needle-like crystals. If you compare the three columns at the right, for example, you see that the SRB may be up to 30% larger than the pixel size. This shows us, for detector selection, the SRB is the decisive performance spec, not so much the pixel size, which is a pure hardware or manufacturing specification. On the other hand, the pixel size influences other properties such as efficiency. So do not focus just on the minimum pixel size, always take into consideration the real SRB and also the other detector specs. In any given X-ray system, the size of the X-ray source gives the second contribution to image unsharpness. Knowing that quantity, in addition to detector SRB, we can, as we shall see, predict the total image unsharpness by calculation. In microfocus systems, we may even adjust the tube such that the tube influence is limited to the desired extent. Again, we would like to know something about your experience. Have you been aware of the difference between pixel size and basic spatial resolution, SRB, of the detector? To understand the concept of focal spot size, first have a look at the X-ray tube. The electrons emerge from the cathode and are accelerated by the acceleration voltage UACC towards the anode. In the anode, there is an inlay, in most cases made of tungsten, onto which the electrons impinge. This part is called the target. The yellow area, which is actually hit by the electrons, is called the focal spot and represents the actual X-ray source. Now the question is how to measure the size of this focal spot. We start by calculating the magnification because we will need this later. By definition, magnification is the ratio of image size and object size. Here in this diagram, we see that object and focus, as well as image and focus, form two similar triangles because all the angles are the same. And from this we conclude that magnification, that is image size over object size, is equal to FDD, focus detector distance, over FOD. So we can say magnification V is FDD over FOD. Now we do a similar analysis of the unsharpness effect. If the source has a certain size phi, this causes a geometric unsharpness on the detector around the edge of the object of size UG. We now try to calculate UG. Again, we find two similar triangles, here highlighted in yellow. On the left-hand side, we have the triangle consisting of the source size phi and the side A. And on the other right-hand side, we have UG and the side B. And if you look at it, we see they are similar, have the same angles, and so we can say UG over phi equals to B over A. Now we investigate how A and B are related to FCD and FOD, which both together give the magnification. We look at these two triangles again, which involve A and B, FOD and FDD. And this leads us to the following equation. UG over phi is B over A. We had this before. This equals to FDD minus FOD over FOD. And this is equal to magnification minus 1. So we can write UG is equal to magnification minus 1 times phi. From this, we see, by the way, that at magnification 1, the spot size causes no unsharpness because this term here becomes 0. To find the effect of the geometric unsharpness in the image, that is to say in the object scale, we need to divide UG by the magnification of the system and get UG image is UG over magnification. So we could now calculate the focal spot size from the unsharpness already. However, for practical reasons, one might use a very small object such as a pinhole, and then we see the unsharpness directly because the size of the object is almost 0. In this case, in fact, the image is a magnified image of the focal spots, so-called point projection or camera obscura image. Thus, we can evaluate the image and directly calculate the focal spot size. In order to achieve repeatable results, all parameter and apparatus data are precisely defined in the standard. On the left-hand side, here for illustration, you see an experimental setup for focal spot size measurement. At the top, we have the X-ray tube in orange. On the stage below, the pinhole camera and the film, which is this red object here. In the middle, you see the camera with the pinhole on top and the fluorescent screen on its bottom. On the right-hand side, you can see that we measure the effective focal spot as it appears under the X-ray beam angle. This makes sense because this effective spot causes the unsharpness in the image. We also see on the X-ray film here below that the focal spot is not rotationally symmetric. This is described and documented by giving two individual specifications for X and Y direction. The image of the focal spot is evaluated then by a modified version of Claasen's method as described in the standard. We take a digital profile in X direction with a virtual slit aperture, which is integrating over the Y direction. Then we integrate the resulting hump here in the middle in X direction to yield the edge response function. The slope of that function is evaluated by finding the 16 and 84% point and then extrapolating it to 0 and 100%. This gives the focal spot size times magnification. The same will be repeated in Y direction to get the Y extension of the focal spot. Another non-digital method would be just to draw a box around the focal spot image to quote X and Y diameter. The question now is what exactly means draw a box, and we shall see. As a threshold for the box position, usually the 10% intensity level is defined. Typically in our calculations, we model the focal spot as a bell-shaped intensity distribution, since it has many mathematical benefits and it's not too far from reality. In practice, the intensity distribution of the focal spot might rather look like a rectangle. This may limit the accuracy of calculations based on this model. Actually, as we saw on the image, it is rather shaped by the filament or the electron source, so it might look quite irregular. Especially the wings of the distribution may lead to discussion which threshold is appropriate. This may be important for acceptance procedures. Since we know now main system parameters contributing to unsharpness, we can calculate the total unsharpness starting out from these parameters. As we see on this drawing, the geometric unsharpness, UG, interferes with the detector SRB, which is mainly caused by the pixel size, in the X-ray image to form the total unsharpness, UT. To gain the total image unsharpness on the object scale, which we call UT image, we need to divide UT by the magnification V. Hence, to calculate this, we also need FDD and FOD. To calculate UT image, ASTM E1000 recommends this formula here. The total image unsharpness is the cubic root of the sum of the cubes of the contributing unsharpnesses divided by the magnification. Under the root, we can easily substitute the formula we found for SRB and UG to get the formula at the right. The corresponding ISO standard gives a similar concept, but we're using squares instead of cubes. This is mathematically justified by the theory of convolution, assuming bell-shaped distributions, as I explained before. The ASTM stayed with the cubes for the sake of continuity. However, the difference is not very large, as we shall see on the next slide. But first, an example. In the beginning, we looked at the images of different quality. Here we show the related figures. The only difference between the exposures is the focal spot size phi. In microfocus tubes, we can easily adjust that. We increased it from 50 microns on the left-hand side image to about 300 microns on the right-hand side image. At the bottom in the tables, you find the calculated values per ISO formula. While at the left image, the unsharpness is only 20% of the wire diameter, at the right image, the unsharpness dominates the wire image by far, as expected. You see, we have here the UT in the image is only 34 micrometers caused by this small focal spot size, and here this big focal spot size causes an unsharpness in the image of 280 micrometers, which is bigger than this wire of 156 micrometers. So in this way, for any combination of tube and detector, we may calculate the expected total unsharpness as a function of the focus object distance if we know the distance from the tube to the detector. It does not make a big difference whether we use ASTM or ISO formula. As you see, the difference here is maybe 10% at most. I have plotted here two examples just to have an idea how this works. So for example, for set 1, we have a focal spot size of 400 micrometers and an SRB of 200. And you see the best position to where we have the best unsharpness is here in the middle, roughly. And if we have this other combination here of a quite big focal 1 millimeter and an SRB of 100 micrometers, we would rather go closer to the detector where we have very little magnification, but where the impact of the big focal spot is minimum. And this is the way you can use this formula. Instead of plotting these diagrams and looking for the best position, you can directly calculate the optimum FOD and the optimum magnification. We just calculate the derivative after FOD or magnification and determine the zeros. And we find the sample position and magnification for the sharpest image. Here you just insert your parameters and get your optimum sample position with these formulas. As we saw, the measurement of the focal spot size is not so simple to perform. However, our knowledge now enables us to determine the focal spot size indirectly. If we have a measurement result for the total image unsharpness or the total unsharpness, it is easy to calculate the focal spot size just by resolving this formula for phi. And moreover, the detector SRB changes only little over time and is even specified by the manufacturer. So by total unsharpness measurements, you could find a tube malfunction or a change of the focal spot size in any way too. Up to now, we talked about the inevitable contributions to unsharpness by tube and detector. But there may be other contributions too, which are more to imperfections of the system or of the scan or of the exposure or to disturbance or any other influences of the environment. And this is what I would like to cover here in this last chapter. But before I do so, I would like to know, would you be interested in part number 2, noise and contrast, to get a more complete overview on image quality? Up to now, we investigated an idealized system which consists only of detector and focus spot. In reality, there are further effects which may increase the unsharpness. These may mechanical or electrical drifts, vibrations, imperfections of the manipulator, and so on. These can be just put as additional terms into our formula and also may be estimated in this way by just resolving this formula in the appropriate way. One thing is often forgotten in computer tomography. Also, data processing, and namely the reconstruction process, may have a remarkable influence on the total image unsharpness. So if you use different algorithms and try to compare the results, don't confuse this effect with system malfunction. The differences may amount to, say, 40% of the image unsharpness. Let me summarize. It is important to be aware that by definition, total unsharpness is 2 times basic spatial resolution. This may sometimes cause confusion while comparing spec sheets and so on. The determination of total image unsharpness in radiographs is standardized. For CT slices, there is ASTM E1441 plus E1695. The new version will be published soon. Mainly focus spot size and detector SRB make up the total unsharpness. It can be predicted by the formula we spoke about. The detector SRB is the decisive resolution performance spec for the detector. It is possible to measure or at least estimate the focus spot size indirectly. Other influences on sharpness, such as drift, vibration, and processing, should be considered too while evaluating a system. This was part 1 on resolution and unsharpness. There may be a second part on contrast and noise, which mainly limit detectability together with the unsharpness. Thank you for your attention.
Hello, everybody, and thank you for joining today's Elements of Image Quality webinar hosted by Dr. Holger Roth, Senior Training Manager, Industrial Radiography at Waygate Technologies. We hope you find the webinar of interest, and we'll start now opening a Q&A session. So if you have not yet submitted your question, do not hesitate, please, to do that. So we have a bunch of questions here. Let's start from the first one. There is a question coming from Mr. Clare saying, is this applicable for nanofocus tubes due to scatter, diffraction, spot position variation?
Yes, hello, good evening or good morning. I'm Holger. I'm trying to answer this question. You saw just before, I think in the last slides, your question came in a little earlier, that you can just add in this formula other terms. So, for example, if you suspect a focus drift, you could just measure your resolution as I described, and you could then calculate how much, for example, such a drift is causing in terms of additional unsharpness or unsharpness, yes, or how much it diminishes the resolution. For diffraction and scatter, you see, this is a totally different question. This is mainly a matter of the object and say of the possibly also of the detector. The unsharpness or resolution is only a geometrical property of the system. So it's not affected neither by noise nor by such phenomena, except they are always there. So for example, if you would say, okay, in the detector there is something which somehow blurs the image, this would be, for example, could be diffraction, yes, a bit. But in general, these image features which come from the object are not included in unsharpness. And I think the other part of your question hints to, or goes in the direction whether it's also possible for nanofocus. There is a standard, it's ISO 12543-5 for small focal spots, say down to 5 microns or so, which requires a wire. I try to perform it, it's possible, but if the focal spot is even much smaller, it's not applicable anymore. But I know there's a standard under development, but I think it will take 1 or 2 years until this will be released for nanofocus tubes. I hope this could answer the question so far.
Thank you very much, Holger, I was going to say. We have another one here which says, do all X-ray suppliers use these methods when stating the image resolution on their product brochures? And if not, how do I compare potential X-ray machines to another?
I would say the X-ray suppliers use the part on the tubes. If it's the normal X-ray tubes, closed X-ray tubes for high power, I think they would all use this standard because it has or something very close to that, because this is a very long tradition. For the detectors, it became now quite normal to quote the SRB, because this is how the resolution of such detector is defined, but you will not always find it, I guess, in the brochures of the systems. They would rather quote the pixel size. You know, the problem seems to be that there is a large variety of customers, and something like the pixel size is very easy to understand and always requested, and the SRB is something you more discuss in a personal conversation or in a more detailed data sheet, but not so much what you just write on a piece of paper, because it is, as you saw, the definitions are not so simple. And whether they all do this, I don't know, but this seminar should put you in the position to ask for that, because these are the definitions which are in the standards, and I think it is a good idea to ask for that, so that you really compare the results. This is the purpose of these standards. I hope this could answer that so far.
Okay, so then we move into the next question that we have, which is, why is modulation transfer function, or MTF, evaluated for 10%, but the duplex wire gauge modulation at 20%? Would you please explain that?
Yes, this sometimes confuses users who use both CT and standard radiograph, because for the one you use ASTM 2002, where you look for the 20% modulation, and if you use CT, you might use the modulation transfer function, which is evaluated for 10%. This sounds not consistent, or sounds not to be not consistent, but the point is that it's something completely different in a way, because in the MTF you always compare to the spatial frequency 0, where you have a very coarse structure, so very wide bars, and which is considered 100%. And if you look, if you do the ASTM 2002, the modulation of the bars, you have no 100% reference. So you only look for the development and look where it goes down to 20%. And there is a publication from the BAM in Berlin a longer time ago, which shows that the equivalent is, I think, something like 80-point-something%. So they made it 20. And so it has been shown mathematically and physically, experimentally, that about that 10% MTF is about 20% modulation in the duplex wire gauge. So it's no contradiction. It's just like it is, and it's not so easy to show, but it is like this.
All right. Thank you very much for this answer, Holger. I will jump into the next one, which says, will the image noise have an influence on basic spatial resolution, or SRB, or MTF?
I think we had a similar question in the very beginning, where I explained that the unsharpness or basic spatial resolution is just a geometric function of the whole system setup, so of the focus spot size and of the distances and of the detector SRB. And so we may say that the noise has no influence. The problem is why this is always confused. The noise reduces or diminishes the detectability of a feature, but it does not mean the image is unsharper. It just makes the contrast of the feature we want to see in the image less visible, or it is somehow disguised by the noise, and so the image looks like if it were not sharp or not really clear. But this is the reason why we make this difference between sharpness and, as we shall later see in the second part of this lecture, the contrast to noise ratio. So it is not affected and no influence on the sharpness itself, because the method is made such that the sharpness is, if possible, independent of the noise. So the noise is cancelled out by averaging, summing up or so.
Okay, thank you for your extended answer. So we jumped into the next question, which says, why is the image noise so important for detectability too, as you said?
Yes, I always mention this because this will be the second part of these lectures, hopefully one day. And the point is, it is so important because the ratio between the contrast and the noise, simplified spoken, is the answer to the question whether a feature may be visible at all. All what the sharpness does, it diminishes the contrast, so that the contrast to noise ratio gets worse. And this question is interesting insofar as quite often users are totally focused on sharpness, especially in the microfocus world, whereas the contrast to noise ratio is a little bit underestimated, but it's so to speak, it's the precondition that you can resolve something. If this is not given, you wouldn't see something even with anything with the sharpest system. And so quite often people forget a bit while looking for sharpness, also to look for the detector efficiency and the signal to noise ratio. In other words, for the time you need to make a reasonable image. And this is the point why I always hint to that it is also important, or minimum as important as the sharpness. So see, there are some further questions coming in.
Yes, we have more. There's another one which says, can the detector basic spatial resolution and X-ray focal spot size change with the system usage?
It can. It depends on the tube. If you have a microfocus tube, for example, between the maintenance intervals, the tube may be dirty or so, and the focusing may be not accurate anymore. You could adjust that or leave it to the maintenance service. So it might degenerate, especially for the very highly resolving. For the bigger tubes, I don't know so much, but I guess it can change something sometimes by the end of the lifetime. But I would be happy to ask my colleagues to clarify this in more detail for the different tube types. So it can, but I'm not sure whether it's. I think it's for the standard tubes, it's not such a frequent thing. For the microfocus tube, it may happen because they are more sensitive to contamination and to aging or whatever, yeah, misadjustment, and so it may happen. So this is the reason why you can check it.
Mm-hmm. Mm-hmm. Let's jump into the next one then. The phantom disk that we have to use to measure the MTF according to ASTM E1000 has to have some specific characteristics in terms of minimum dimensions of the disk and material.
Not really. In the standard, and the new version will hopefully be published soon. I hope by end of the year or earlier. But already in the current version of the standard, you see that it says it should have an application-specific diameter. So the material thickness should be in the range what you want to investigate in your tests, and it should be I would say it should be, or I must say, it must be penetrable. So you have to have a reasonable disk image, otherwise the mechanism will not work. And it needs to be round. So round means it needs to have a good circularity. So it should not maybe deviate from a circle more than the tenth of a pixel, roughly. Or not of a pixel, of a voxel. And then it works quite well. You can choose any material in principle. What you can often use for many systems is, for example, if you do the typical castings, maybe you would use 2.5 inch of aluminum, for example. For titanium or something like that, you might maybe look for this wall thickness, typically maybe 1 centimeter titanium. I did not try it out. By the way, these rods are easy to get. You can buy them. I don't want to make an advertisement here. For example, I think in America the company is named McMasters. It's around $50, and you have such a rod which is round enough, typically. And you can test it whether it's round enough and try it out. So.
Okay, thank you. Yeah, we have a couple of more, and I also invite the attendees to, again, don't hesitate to share your questions via the chat if you wish. But let's jump into the next one then. Are line par gauges down to 1 or better sub-micron available to compare image quality?
They are not. So I would say there is no line per gauge exactly as the one I presented to you, which is so fine, because nobody managed up to now, I think, to make such fine wires and arrange them in the same way. But what we use sometimes, there is a gauge made by the Japanese organization JIMA, and it is a plate, I think, or a foil out of, I think it's carbon, and there are gold bars on it, and they go down to, if I remember right, 0.5 microns. So this typically is enough to check a microfocus system, and I tried it out. It works quite well. I could not cross-check it to other methods because there is nothing real useful. But what I did ASTM 1695 measurements for determine the MTF at 10%, and then we know the detector SOB, we know the magnification very precisely, and so I found that the focal spot sizes I determined by using this pattern really fit into the whole theory, you know, with this formula with the squares and the cubes and the square root. So you have the detector SOB, you have the magnification, you have your measurement of the total unsharpness, and you have the measurement of the focal spot size using this JIMA pattern, and all things that really were consistent and fit together. So I think it's a useful tool to at least check the consistency or the constancy of your focal spot size. And it is easily available. The price is something around, say, roughly $1,000, and you can just order it by mail. If you need more details, you may give me a mail or so.
Thank you, Holger. Next question that we have is, does focal spot size have an effect on basic spatial resolution, or BSR?
Sure, it has. If you look back into this script here, and you may have also a mail from me if you like. By this formula where you read the total spatial resolution is the square root of the detector unsharpness plus the tube unsharpness divided by the magnification. You see that it has an influence, except magnification 1. So in the classic radiography where you put your sample directly on the detector, the focal spot size has no effect. But as soon as you use magnification, as in tomography, you need to use magnification because you need to rotate the sample, and the sample also has a certain extension. It has an influence, and it is remarkable. Yeah. So
okay, good. So one of the last questions we have, in fact, is this one. Is the filament aging affecting the resolution? And if yes, what will the standard aging time of microfocus filament in idle or non-usage time?
Just let me read it again, because it should be a little more complicated. I think the person who asked the question is talking about microfocus filament, microfocus tubes. I would say it can affect the resolution as insofar as maybe close to the end of the lifetime the filament may distort, yeah, and then maybe it changes slightly, but it's not to my experience it's not a big change. What can happen rather is that maybe that the tube after a long time without maintenance, it may be maintained and readjusted because they drift a bit after a while. But I think the effect is not too big. For the high power tubes, frankly, I don't know, but as in the question before, we will find out that whether it changes a lot. But I think it does not change a lot. So, because, you know, if you would really need to change the filament a lot, and if you do that, it will break. So this is the reason why I would exclude that. It's rather, for the microfocus tube, it's rather the adjustment of all the lenses and the geometry inside.
And one more question that has came up is, what parameters do you suggest to monitor in order to guarantee that system performance are repeatable in terms of image quality?
So in a CT system, I would recommend just to use this ASTM E1695, apply it at the position where you normally do your scans, or maybe at different positions if you have, say, different favorite position, maybe a very high magnification, very low magnification, and a medium magnification, or whatever you do. And then you should see if there is a change which is relevant for your images, for your scans. In the same for standard machines, they quite often use ASTM 1695 E2002 and use the duplex wire gauge and check the total image resolution at this position. And anyway, for many applications, it is prescribed to use image quality indicators which check both, so to speak, detectability, that is noise and contrast, and the resolution. Classically, what you do, you check on a regular basis the focal spot size of your tube and the focal and the detector SRB, and as I will show in the next lecture, also something concerning the noise, some measurements concerning the noise, and that's it. So if you check detector SRB and tube SRB, tube unsharpness, that is the focal spot size, and maybe the sharpness at the position where you are, either with the rod or with the duplex wire gauge, depending whether you do radiographs or CTs, then I think you're on the safe side because you would detect the change and would even know where it comes from. Please keep in mind, in CT, the change also may come from the movement of the rotation table, and this is only included if you use this rotation method, so this ASTM E1695.
Thank you very much, Holger, for your response. In fact, it's just 1 minute to go, so we don't have more questions here to go through. It seems that we covered them all. Of course, in case you didn't manage to send your question, or we didn't manage to answer pending ones, do not hesitate to contact us. Once again, we want to thank you for your time today, and we wish you a really good day ahead. Thank you very much.
Thank you. Have a nice day or evening.